Here we represent the interference pattern on the x-axis, where at O we have the central fringe, which is a bright fringe of abscissa 0. Now we are going to associate to each interference fringe its corresponding abscissa. This bright fringe corresponds to k equals to 1. This is the abscissa of bright fringe of order k. Then the bright fringe of order 1 corresponds to k equals to 1. Thus, x equals to lambda d over a. Which is on the positive side. The bright fringe of order 2 corresponds to k equals to 2, and we write 2 lambda d over a. Of order 3, 3 lambda d over a. Now for order minus 1, we write minus lambda d over a. For order minus 2, we write minus 2 lambda d over a, minus 3 lambda d over a, and so on. Now for dark fringes. The dark fringe of order 0 corresponds to k equals to 0, which is lambda d over a. So where is this dark fringe? This dark fringe is found here, having an abscissa lambda d over 2a. We obtain its abscissa by replacing k by 0 in the expression. The center of the dark fringe of order 1 corresponds to k equals to 1. And we obtain 3 lambda d over 2a. This is the dark fringe of order 0, so k equals to 0. Here k equals to 1. And here k equals to 2, so we write 5 lambda d over 2a. What about the dark fringe of order minus 1? So we get minus lambda d over 2a for k equals to minus 1. This is minus 3 lambda d over 2a for k equals to minus 2. Here k is equal to 1, k is equal to 2, k is equal to 3. Here's k equal minus 1, minus 2, and minus 3. Note that the central fringe corresponds to k equals to 0. It is a bright fringe of order 0. This is called the first bright fringe. This the second bright fringe, and this the third bright fringe. These fringes are from the positive side. From the negative side, this is the first bright fringe as well. This is the second bright fringe, and so on. In the same manner, this is the first dark fringe. This is the second dark fringe. These are also from the positive side, whereas these are from the negative side. This is the first dark fringe, this is the second, and so on. We are going to mention a very important thing. The first bright fringe corresponds to k equals to 1 or k equals minus 1. The second bright fringe corresponds to k equal 2 or minus 2, and so on. But the first dark fringe corresponds to k equals to 0 or minus 1. This is the second dark fringe, and this is also the second dark fringe. On both sides, the second dark fringe corresponds to k equals to 1 or k equals to minus 2, and so on. Let's summarize so far. The first bright fringe is the bright fringe of order k equals to plus or minus 1. The second bright fringe corresponds to k equals to plus or minus 2, and so on. But the first dark fringe corresponds to the dark fringe of order 0 or minus 1. The second dark fringe corresponds to k equals to 1 or minus 2, and so on. This is a very important note. Now we're going to solve an application on the previous ideas. Consider Young's setup. The distance between the two slits is 0.2 millimeters. The distance between the plane of the slits and the observation screen is 2 meters. The radiation we are using has a wavelength of 630 nanometers. The source S is found on the perpendicular bisector of S1 and S2. This means that SS1 equals to SS2. We have 2 points on the observation screen on both sides from O, where S2A minus S1A equals to 3.15 micrometers, and S2B minus S1B equals to minus 1.575 micrometers. The first question is, specify the interference fringes at A and B, or in other words, we have to specify the nature of the fringe that is found at point A and that at point B. Note that the nature of a certain fringe is specified by the optical path difference. For point A, delta A equals to SS2A minus SS1A, which is equal to SS2 plus S2A minus SS1 minus S1A. SS2 is equal to SS1. We can eliminate them both. We obtain S2A minus S1A, which is equal to 3.15 micrometers. And this is the optical path difference at A. If the optical path difference delta is a multiple of lambda, we obtain a bright fringe. If it is an odd multiple of half the wavelength, we obtain a dark fringe. So let's divide the optical path difference by lambda. We obtain 3.15 times 10 exponent minus 6 over 630 times 10 exponent minus 9, of course in SI units, and the answer is 5. Delta A over lambda is equal to 5. Then delta A is equal to 5 lambda, which is actually a multiple of lambda. Therefore, A is the center of the bright fringe of order K equals to 5. This is K. In the same manner, we proceed to find the nature of the fringe at B. We can verify that delta B is equal to S2B minus S1B, which is equal to minus 1.575 micrometers. Dividing delta B by lambda, we get minus 1.575 times 10 exponent minus 6 over 630 times 10 exponent minus 9, which is equal to minus 2.5. Or it is minus 5 over 2. And as a result, delta B over lambda is equal to minus 5 over 2. Therefore, delta B is equal to minus 5 lambda over 2. Note that minus 5 is an odd number, then the optical path difference is an odd multiple of lambda over 2. Then B is the center of the dark fringe of order k equals minus 3. How did we find k? This minus 5 is actually 2k plus 1. Thus k equals to minus 3. In the second part of the question, calculate the abscissas of points A and B, with the x-axis being directed upwards. So how can we determine the abscissas of A and B? We use the following formula. S2m minus S1m equals to AX over D. Note that S2a minus S1a is equal to AXA over D. We use the path difference of A to find the abscissa of A. XA is equal to S2a minus S1a times D over A, which is equal to 3.15 times 10 exponent 6 times 2 over 0.2 times 10 exponent minus 3. And the answer is 3.15 times 10 exponent minus 2 or 3.15 centimeters. Similarly, to determine the abscissa of B, we use S2B minus S1B equals AXB over D. We proceed to find XB, which is equal to minus 1.575 times 10 exponent minus 2 or minus 1.575 centimeters. Part 3. In the third part of the application, we have to calculate the abscissas of the centers of the bright fringes of orders 4 and 5 and those of the dark fringes of orders minus 1 and minus 2. How can we determine the abscissas of an interference fringe in general? We always use the optical path difference, delta, which is equal to SS2m minus SS1m. Now, since S is equidistant from S1 and S2, this becomes S2m minus S1m. We have previously shown that this is equal to AX over D. Now we know that delta equals to K lambda corresponds to the center of a bright fringe of order K, where K is an integer. So AX over D equals to K lambda, and we obtain X equals to K lambda D over A. This is the abscissa of the center of the bright fringe of order K in general. Now for the bright fringe of order 4, K is equal to 4. Then X4 equals to 4 lambda D over A equals 4 times 630 times 10 exponent minus 9 times 2 over 0.2 times 10 exponent minus 3. The answer is 2.52 times 10 exponent minus 2 meters or 2.52 centimeters. The abscissa of the bright fringe of order 5 corresponds to K equal 5. So X5 equals to 5 lambda D over A, which is equal to 3.15 centimeters. Now for a dark fringe, the condition K lambda changes, but the analytic expression of delta is always AX over D. So for a dark fringe, delta equals to 2K plus 1 lambda over 2, where K is an integer that corresponds to the order of the fringe. The optical path difference is always AX over D, which is equal to 2K plus 1 lambda over 2. We obtain that X equals to 2K plus 1 lambda D over 2A. And this is the abscissa of a dark fringe of order K. Now to avoid confusion, we're going to assign the letter B for the abscissas of bright fringes and D for the dark fringes. So what is the abscissa of the dark fringe of order -1? This corresponds to K equals to -1. Then XD minus 1 equals to minus lambda over 2A. The answer is minus 3.15 millimeters. For the center of the dark fringe of order -2, we replace K by -2 and we obtain minus 3 lambda D over 2A. Which is equal to minus 9.45 millimeters. In part 4, calculate the distance between the centers of the bright fringes of orders 4 and 5 and that between the centers of the dark fringes of orders -1 and -2. We're going to start for the bright fringes. This distance is D, for example, which is between the bright fringes of orders 4 and 5. What is the distance between 2 points on the x-axis? This, for example, is the center of the bright fringe of order 4. This is x4. And this is the center of the bright fringe of order 5. And this is x5. Here is the distance between these two dark fringes. D is equal to x5 minus x4, which is equal to 3.15 minus 2.52, and this is equal to 0.63 centimeters. Now what is the distance between the dark fringes? It is equal to the larger abscissa minus the smaller one, which is x minus 1 minus x minus 2, which is equal to minus 3.15 plus 9.45. The answer is equal to 6.3 millimeters or 0.63 centimeters. What can you conclude here? Note that the distance between two consecutive bright fringes is equal to the distance between two consecutive dark fringes. This conclusion verifies the experimental observation, which says that the interference fringes are equidistant.